Hey y'all, it's your main math teacher, Mr. Boyden, back at it again today because today we're going to be doing the rational root theorem. So to put this in context, let's consider what we already know. We know how to solve quadratics, we know how to factor some but not all polynomials. We can use division to test the zeros, whether it's long division or synthetic division, and once we've done that, we can use end behavior and zeros and multiplicity to sketch the polynomial. So today what we're looking at is what if we don't have a seed zero? And what I mean by that is in the previous video we had an equation, and we were also given some piece of information like 2 is a zero of this function. Then we'd use the 2, we'd reduce down the degree, and we'd proceed. But what about when we're not given that? So before we get into the rational root theorem, we first need to recall, what does rational mean? Okay, rational is any number that can be expressed as a over b, where a and b are integers, and b is not 0. Okay, so that's a little bit fancy sounding, but all that means is that it's a number that can be expressed as a fraction. So take, for example, 12. Can 12 be expressed as a fraction? Certainly. 12 over 1 or 24 over 2. So yeah, it can be expressed as a fraction. What about 5 halves? Yeah, absolutely. That is a fraction. That fits the definition almost perfectly. What about a number like pi? No, pi cannot be expressed as a fraction. There are rational approximations for pi, but you can't actually do pi as a fraction. Same thing with like root 3 or most radicals. So those do not count as rational numbers. What we're going to see today is my paraphrasing, actually, of the rational root theorem. I'm going to, for the purposes of this video, and you're welcome to look it up, but for the video, I'm going to spare you the longer definition. Basically, what we do is if we want to find the rational roots of any polynomial, all we're going to do is take the factors of the constant term, and then we're going to divide those by the factors of the leading coefficient. That generates a list of possible zeros. It doesn't mean they are the zeros, but it means if there's rational zeros, then they're going to be in that list. Then what we're going to do is we're going to test those with synthetic division. So let's do an example, and we're just going to go slowly through this. Okay, to find the rational roots, take the factors of the constant term. Right, factors of the constant term. So what are all the factors of 125? It's divisible by 1, it's divisible by 5, it's divisible by 25, and it's divisible by 125. Okay, I think we got that. Check. And divide them by the factors of the leading coefficient. Okay, our leading term is down here, so our leading coefficient is 1. Okay, and we're supposed to divide that first set of numbers by the factors of the leading coefficient, and that generates a list of possible zeros. What I like to do is actually write the word list for this. Okay, so I'm going to get a list of possible zeros. So that would be 1 divided by 1, which seems a little trivial. They'll get more interesting in a minute. And 5 divided by 1, which is 5. And 25 divided by 1. And 125 divided by 1. Okay, and then the other thing, and this is easy to forget, but technically 125, or negative 125, it's divisible by negative 1 and negative 5, negative 25, and negative 125 as well. So we're going to have plus minus on all of these, because also the negative versions might be, they are possible zeros. Okay, so here's why they're only possible zeros and they're not guaranteed zeros. Right now, this list has 8 numbers in it. 1, negative 1, 5, negative 5, 25, negative 25, and 125, and negative 125. What is the greatest number of zeros this equation could have possibly had? It's degree 3, so there's no way for it to have more than 3 zeros. So what we have to now do is figure out which of these are the zeros and which are not. So to do that, I'm going to use synthetic division. Now, there's not necessarily a rhyme or reason to which ones you pick. What I like to do, I like to pick the ones that are the easiest, and it looks to me like 1 and negative 1 are the easiest to test, so I'm going to test those with synthetic division now. Okay, so here we go. So I'm going to have a 1, a negative 15, a 75, and a negative 125. All right, so pull the 1. All right, 1 times 1 is 1. Looks like we have negative 14 there, and then we still have a negative 14. 75 minus 14 should be 61, and then pull the 61 up, and you know what? I'm not even going to spend time thinking about that because it's not going to be 0 at the end. So I'm not going to put any more effort into it than that. What I'm going to do is move on to the next number, and that would be negative 1. So we've eliminated one of these 8 possibilities as being wrong, and we're just going to jump right into the next one. Okay, negative 15, 75, negative 125. All right, here we go. Maybe negative 1 will work. Okay, so 1 comes down here to be 1. We have negative 1, so negative 16. So that would be positive 16. So that should be 91 and negative 91. And then I'm not going to do the last step because it's already clear to me that it's not 0. Now, we've tested -1 and 1. They're wrong. We have 6 more to go. Let's test 5. So here we go. 1, -15, 75, -125. All right, so pull the 1. And 1 times 5 is 5. And then we have a -10, which seems like we would have a 50, -50. So we get a 25. 25 times 5 is 125. So hey, look at that. That came out to be 0. So if we're asked to graph this, right now, what do we know? We know that 5 is one of the zeros. Now, we can continue to test 5 and continue to test these other numbers if we want. But what you should always do is double check what the degree of your output is. Okay, we started out with degree 3. This output would mean that that's x squared, and that's x, and that's a constant. So as soon as you get to degree 2, what I would like you to do, because it's most efficient, is stop using the synthetic method and use some sort of method to solve quadratics. And we have 3 of those. We can do just direct algebra steps, we can factor, or the quadratic formula. I have a linear term here, so it's not going to be direct algebra steps. I'm going to try factoring, and if that's reasonable, then we'll go with it. I'm looking for numbers that multiply to be 25, add to be -10, so that seems like that would probably be a -5 and a -5. Nice, that factored. So my zeros are 5 and 5. So what are the zeros in this question? 5, 5, and 5. Could there be any others? No. Okay, we have a sum total of 3 total multiplicity, and we have an m1 right here, a multiplicity of 1 right here, and a multiplicity of 1 right there. So when we go to sketch this, let's come out to 5. At 5, there's a total multiplicity of 3 because 5 is happening 3 times. And that gets a little bit weird. So what we have to remember then is since 5 worked 3 times, what functionally this equation is, it's the same as x minus 5 quantity cubed. So that way 5 is the 0 and its multiplicity was 3. So really this looks like just a basic cubic that happens to be shifted 5 units to the right. Okay, so there is our sketch. Let's try 2 more examples. Now, as always, as soon as you feel like you can do some of this on your own and you don't need to see the tutorial first, pause the video and do what you can. At this point, I'm pretty well just going to cruise through the next examples. All right, here's our next one. We're going to go through the exact same process. We're going to list out the factors of the constant term, 1 and 3. We're going to list out the factors of the leading coefficient, 1, 2, 4, and 8. Then we're going to take these numbers on the right, so I'm going to make a list, these numbers that were factors of the constant term, and divide them by the factors of the leading coefficient. So that would be 1 over 1, so that would be 1, 1 over 2, so 1/2. We have 1 over 4, and we have 1 over 8. Then we're going to take the 3 and divide that as well, so 3 over 1, which is 3. And we have 3 over 2. And we have 3 over 4. And we have 3 over 8. All right, we've got our list of zeros. 1, 2, 3, 4, 5, 6, 7, 8. So really that's 16 because it's all plus minus. It would be very unusual if we had to do all 16 of them, so don't even worry about that. What we'll do is we'll just start testing the ones that look easy. My favorites to test are always 1 and -1, so y'all, you can pick anything you want here, okay? It doesn't matter. You can pick any number in that list. This is just my strategy. Okay, so here I go. 8, -4, 6, -3. Let's see what I get when I do that. So I get a 1, and then an 8, and then a 4, and then a 4, and a 10, and that's not going to be 0. Okay, 1's out. So you see how quickly I just move on to the next one? I don't spend a whole lot of time thinking. It either comes out as 0 or it doesn't. And as soon as I know that, I'm not writing down that last number. It's not worth my effort. Because, and yeah, I mean, 10 minus 3 is 7. That's an easy one. But it's not worth the effort. You already know it's not going to work. And so there's no point writing it out. Okay, let's put the 8 down here. So then we get a -8. So a -12, make it positive, and we get 16, -16. And that's not going to be 0 either. All right, -1's out. Now, there's a little bit of debate here. You could do 1/2, that's pretty easy, or 3 is pretty easy. I'm noticing there's a lot of even numbers here, so I'm actually going to try 1/2 and we'll see what happens. All right, here we go. So 8, half of 8 is 4, -4 plus 4 is 0, half of that's still 0, bring down the 6, half of 6 is 3, so that worked. 1/2 is one of my zeros. Now, what do we want to do? Do we want to use 1/2 again? Do we want to go through these numbers again? Probably not. Okay, what we should probably do is take a minute, realize that's 8x squared plus 0x plus 6. So 8x squared plus 6 equals 0. And you know what? We can solve that by basic algebra means because that term, that linear term, is 0. So here we go. I'm going to subtract 6 on both sides. And we'll divide by 8, so I get x squared equals -3/4. Then we'll take a square root and we'll interpret what that means. What is the meaning of the root of -3/4? Well, it's the square root of a negative number. So what that tells us is there are no real solutions, no real zeros from this little chunk of math. So remember, 1/2 worked. 1/2 was one of the zeros. Now, there's a lot of different questions you could be asked about this. We were just practicing the theorem, so what would be the questions? You might be asked to make a list of all the zeros. Check, we did that over here. You might be asked what all the zeros are. All the zeros, in this case, it's just 1/2. So I'm going to make a note of that. So the 0 is 1/2. There are imaginary roots, so technically these are roots, but for this point in this class, we're only going to write down the real roots. And so we have them right here, and you might be asked to graph, although on this one I'm going to skip it because we've not talked about how to graph imaginary roots. So this one's actually done. The only thing I'd like to add to this is, do you know what the multiplicity of that root is? Okay, and this is where some people get kind of confused because it seems like it would be 3 because the multiplicity has to add up to 3, and it totally does, but this is a multiplicity of 1, and if you consider this equation right here, because of that, a total multiplicity of 2 comes out of here. It's just that it's imaginary roots that each have a multiplicity of 1 adding up to the 2, because that's a little plus minus. So this one has a multiplicity of 1, so at that point on the graph, it would cross over the axis. One more. All right, this one's very similar to the last. Factors of 8 are 1, 2, 4, and 8. Factors of 1 are 1. Make a list. So we have the plus and minus versions of 1, plus or minus 2, plus or minus 4, and plus or minus 8. Pick your favorite number. I like to start with 1, although I can already see 1's not going to work because you're going to have a 1 and a 5. Those won't cancel out, and a 2 and an 8 aren't going to cancel out either. But I'm going to run through it anyway just so you can see. So 1, -5, 2, 8. So pull the 1. 1 times 1 is 1. You get a -4, -4. -2, -2, and that doesn't come out to be 0. It comes out to be 6. So we'll try -1. So here we go. 1, -1, -6, 6, 8, -8. Woohoo! This one worked. Nice. All right, so that works. -1 is one of our zeros. What are the others? Pull this down. X squared minus 6x plus 8. We're going to look for numbers that multiply to be 8 and add to be -6. I think what those are is probably x minus 4 and x minus 2. And so 4 is one of my zeros, and 2 is one of my zeros. And it looks like each of them have a multiplicity of 1. They have to add up to 3, so that'd be 1, 2, 3. All right, we found the zeros. And we got kind of lucky. We only had to do 2 tries on this one, but that's okay. That was actually a good thing. So let's graph it, or sketch the graph of it, I should say. So 1, 2, 3, 4. There's 4, 2, there's -1. End behavior is positive on the right-hand side. Looks like they cross at all these locations, so here's my best quick attempt at a sketch. Make the quick note here that that y-intercept is at 8 because we see that right there. And hey, it's done. So, y'all, with those three examples, you've seen most of the things now that can happen. The only things I'd like to add is these were relatively quick examples. Sometimes you'll have more factors here and you'll have more factors here, so your list of numbers will be bigger. That's okay. You're still just going to test them methodically. They just take a little bit longer, and I thought that would be kind of a boring video. It requires no more skill, just a little bit more perseverance. And then the other thing that happens is if you're dealing with a 4th degree instead of a 3rd, your output here and here will not be quadratic. It'll be cubic. So you get to use these numbers again. Okay, and so then you have to keep testing numbers. And then if you've used -1 and it worked, use -1 again. Okay, so for example, in this setup, we would have gone to our next step and it would have been -1, 1, -6, 8. That's if it had not been quadratic. And granted, on this one, we know that wouldn't work because 4 and 2 are the solutions. But you keep using that root or that possible number until it fails you. For example, -1 failed us, it's done. Okay, so that's basically all the things you need to know about the rational root theorem. Go practice it, have some fun, and we'll see you next time.